In this video, we're going to look at a third kind of accumulator that we can use to support tail recursion in functions that are traversing trees of different kinds. This kind of accumulator may seem to be a bit more difficult, but if we work on it systematically and practice, you can get to do it just as easily as you can do the accumulators we've done so far. As an example, let's go back to the silly House of Black descendant family tree. So in this tree, it's a descendant family tree, so we have a parent that has any number of children, which can each have any number of children, and so on and so on. And all we're going to want to do this time is just count all the people in a tree. So if we call our count function with this top person, we would count all the way down through the tree like this, 1, 2, 3, 4, and so on. Okay, let's get going on it. What I've got open here is the work list ACK starter file, which you can get from the website under week 10. It's got the data definitions that we've seen before for a descendant family tree and some example data for the House of Black descendant family tree. And I've already got a function that does the job we want it to do. Count encapsulates two inner functions, one to operate on person and one to operate on list of person. I've used a slightly different naming convention in here this time. These were originally templated according to the data definitions for person and list of person, and I filled them in the natural way. If we're counting the number of people in an empty list of people, then that's 0. Otherwise, we add together the number of people in the first person in the list and the number of people in the rest of the list. And of course, if we're counting a single person, that's just add 1 to the count of that person's kids. And so that function works. I'll run it right now. The question we want to ask ourselves is it tail recursive? And we can see relatively immediately that it is not tail recursive. There's 3 mutually recursive calls. There's this call to count LOP, this call to count person, and this call to count LOP. And not a single one of them is in tail position. This one's not in tail position. The first one's not in tail position because there's a call to add 1, which is waiting to consume the result of this call as an argument. This one's not in tail position because there's a call to plus that's waiting to consume the result of count person as an argument. In addition, once we evaluate count person, we also have to evaluate count LOP to pass to plus. So none of them are in tail position. But let's start by working on this one here. This one seems a lot less hard because it's really a lot like what we saw before when we converted sum of a list into a tail recursive form. What we need to do somehow is manage to take this call to add 1 and get it into, instead of have it wait for the result of count LOP, we want that work to somehow be passed as an argument to count LOP. And we can do that with an accumulator. Let's go ahead and start doing it. Since this is a somewhat complicated task we're setting out, and we've got a function that already works, let's make a copy of it, comment the old one out, and work on the copy so that if we mess up partway through, we can start again with something that actually works. So again, we're trying to get this add 1 work into an argument, an accumulator argument to count LOP. So let's just add that accumulator. Let's call it so far rather than just ACC because it seems to be something like the count so far. And we know its type right away. Accumulator so far is natural. And we're not going to be quite sure about this yet, but we'll put something like the sum so far, something like the count so far. Okay? And we've got the accumulator there. Since these functions are mutually recursive, if this one's going to have an accumulator, this one has to have the same accumulator. And we'll put some dots here telling us that now when we call count LOP, we have to pass this accumulator. And we'll put some dots here telling us that now when we call count person, we have to pass an argument for this accumulator. And similarly there, when we call count LOP, and the first call to count person, we have to pass something there. Now we know what we're going to pass here. We're trying to get this add 1, instead of happening when the count LOP returns, have it happen as we call count LOP. So really, we're just going to take this add 1, move it there, and say add 1 to so far is going to be the argument for so far accumulator for count LOP. And think about what that's saying now. It's saying, gee, in order to count a person, go count the person's kids and add 1 to the count so far. So we're adding 1 to the count so far to correspond to P, and then going to count the person's kids. So that looks like it ought to work. And we could probably even fill in the initial value of so far to be 0. But what's happening down here? Down here we've really got two problems. The problem isn't just that there's a plus waiting for count person to produce a result. In addition to the plus, there's actually a mutually recursive call to count LOP that's waiting to happen until count person produces its result. So there's a lot going on there that has to happen after count person produces a result. The plus seems to be pretty easy to do later because the plus is just going to add the count of this person with the count of all the other persons. It's really this count LOP on the rest of the LOP that's causing us a problem. But let's look at that carefully. In this whole extra recursive call that happens after count person, count LOP, we know that's going to happen. The part that's really changes on each call is this rest here. Each time we're going to count those particular people or that particular list of people. So what we can do is we can take this rest LOP and actually add it as another accumulator argument to count person. And what that's going to say is it's going to say, look, go count this person right here. Go count that person. And when you're done counting that person, go count these people here. Go count them. So count person is going to get something to do right away and something to do later. Let's try to make that work. We'll take this rest. We'll add it as another accumulator argument to count person. So count person is going to get another accumulator argument. This is to do later. We can call this to do later if we like, or I'll just call it to do. It says after you count this person, go do these other people. And we'll put the count person in tail position now. We'll put something there to remind us that count person now has this extra argument. So now let's see what's happening is that we're calling count person and we're saying first count this person. This will be this accumulator argument, which we still have to figure out what to do here. And then this is going to say then count these people. So let's go look at what we have to do inside of count person. Let's give ourselves a bit more space so it's easier to see. Count person gets told to first count this person, which it does basically by adding 1 to so far. And then it's got to go count these people. But count person calls count LOP and gives it a list of persons to count. In other words, this person's kids. So we could just take the new extra people to count and just append them onto to-do. So now count person counts P, and then it says to count LOP, go ahead and count this person's kids as well as whatever I was told to do after, as well as what I was told to do later anyways. And now we can see that all the actual counting happens here. So the value of the so far accumulator, the count LOP, passes to count person is just going to be so far. We're not going to add anything to that accumulator here. So now there's one thing about this code I don't quite like, which is the two accumulator arguments are in this order, so far to do here. And here there's this list of people, and so far they're kind of in the other order here, and they have different names. So I'm going to do two things. I'm going to make their names consistent, and I'm going to put them in the same order. First, let me just provide the initial value of the to-do list, which is empty. And I can use Dr. Racket has a feature that will let me rename an argument. I click check syntax first, then I click write on the parameter. I click rename for the parameter, and I'm going to call this to do as well. And what Racket doesn't have is a built-in feature to allow me to reorder the parameters of this function. There are some programming environments that do that, but Dr. Racket isn't one of them. So this part I'll have to do by hand. Let me work very carefully. I'll reorder the arguments here, and then I'll go find every call to count LOP. Here's one, and I'll just change the order of the arguments there. And that's the only call to count LOP. So now it looks like I just about have this. Oh, there's one thing I have to do here, which is this result. At the end of the day, when I'm completely out of people to count, the result I want to return now is not 0, but rather the value of the so far accumulator. Let's try it and see if it runs. All 3 tests pass. Now we can get quite clear in our mind what the invariant is for, let's see, the so far accumulator is the total number of persons counted so far, and the to-do accumulator, well, that's a list of person. And what invariant is it? Well, it's a little bit tricky what it is. Let's look at where we add to it. What count person does is it says, look, however many people had been put on the to-do list so far, I just add this person's kids to it. So as we go along, to-do gets bigger and bigger by adding every node we visit's children to it. And then the to-do accumulator gets shorter right here, where we take the first thing in the to-do list and go count it and keep only the rest of the things to do. So what this accumulator is it's all the children of persons we have visited that have not yet themselves been visited. So every time we visit a person, we add all that person's kids to do, and then one by one we take them off to do as we go. At the end of the day, to do is going to be empty. So that accumulator may seem a little bit more complicated, but what I suggest you do is watch the video one more time and then practice doing it. The basic intuition is really no different than the other tail recursion accumulators we've seen. We had some work that was surrounding a mutually recursive call, so we didn't have tail recursion. We took that work and arrange to pass it in, pass the result of that work in as the value of an accumulator in the mutual recursion. That's the first thing we did, and that's really just like sum and count operating on lists. Here, we had some work that was going to happen after a recursive call, after a mutually recursive call. So we couldn't pass the result of that work into the mutual recursive call because here you have two mutually recursive calls. One of them has to come before the other one no matter what. So what we did in this case is instead of passing the result of this recursive call in as the value and accumulator argument to that recursive call, we instead passed the work list for this recursive call in as an argument to this mutually recursive call. So you've got two very different kinds of accumulators here. So far is an accumulator that's accumulating work that has been done. It's accumulating every person that's been added up so far, every person that's been counted so far. To do is a very different accumulator. To do is accumulating a list of persons that still need to be visited. It's saying, look, when we finish with this call to count person, we got to go visit these persons. This kind of accumulator is often called a work list accumulator because it's a list of work remaining to be done. And it's quite different than so far, which is a result so far accumulator. But both of them are built on the same intuition, and it takes both of them in order to make a tree traversal tail recursive.